Hello and welcome to this episode of Math with Martinez. We are in our Algebra 2 Unit 9. This is the first video in this series, all on exponential functions and equations. And we are looking at graphing exponential functions here today. So I want to begin by diving into this question. Would you rather? Would you rather have $300 added to your account each year, or have it earn 3% annual interest? Well, the answer to that depends on the amount that you invest initially and the duration of the time that it's in the investment. When a quantity changes by the same amount during a period of time, it's modeled by a linear function. That same amount is changing by a common sum, or it might be decreasing and therefore changing by a common difference. And so for this scenario, what would model that is to have a function, we'll call it just f, and it depends on time. Each time that we're working here, we're taking 300 and multiplying it with the amount of years and adding to that the principal amount, the amount that was initially put into your account, which isn't specified, but you can see here that this is a linear function with an initial amount and a constant rate of change. That's your slope of 300 each year. However, when you see a quantity changing by the same factor each time or multiplying by the same amount each time, that is what we call an exponential function model. Again, I'll repeat that. It's changing by a common factor. Or you could say multiple. Each time it's multiplying by this same amount. And so we could call this function, let's give it a different name, we'll call it g. It again depends on time, but what's happening here is we're taking a principal amount and we're multiplying it by the initial amount, or 1, plus our rate that we're earning each time, which is 3%, expressed as a decimal is 0.03. We're adding to our principal amount that interest rate, and it's growing according to t. So which one would you rather earn? Well, think about it this way. This one is going to be growing at a linear rate, which, is good to begin with. It looks really nice. If you're starting here with your f function, it's going to start at some amount and go by 300. So this might be your f function. And your g function is going to start also at that initial amount, and then it's going to grow more slowly, but then something's going to happen and it's going to really take off exponentially. So which one's going to be better for your account? If you haven't guessed it, it's going to be G. You would like to earn interest over time more than just adding the same amount each year. And that leads us into our discussion on a new type of function, the exponential function. A function is an exponential function when it's written in this form, where b has to be greater than 0 and b cannot be equal to 1. And there are several standard exponential functions that we're going to cover throughout this unit. And the first is this one that you see here. It is sometimes referred to as the binary base exponential function because its base is 2. This ends up proving very useful, as we do often work in a binary system when we're dealing with computers and coding and working with zeros and ones. So it is very frequently seen, this exponential function with the binary base of 2. So let's go ahead and graph that function. If you don't have your graphing calculator, make sure you grab that now, or grab a digital version of one, so that we can go ahead and graph this function and look at some of its key features and see just what this graph looks like. Go to y equals, and we'll go ahead and type in 2, and we'll raise it to the x power. Make sure that you select the x, that is the variable key next to your alpha button. Otherwise, your graph will not look like this. That is the graph of the exponential function. It starts off really slow and looking almost flat, and then it grows at a tremendous rate. We're going to go ahead and go to the table so that we can see some important values. You can see here at -10, -5, I mean, all these values, it is just like almost zero. So if we're going to draw this graph, let me grab my color here. If we're going to draw this graph, it looks like it's almost at, like on top of the x-axis. But then something starts to happen right about here. At -2, it's at 0.25. That's at like about a quarter. I'm going to zoom in here. Maybe something like that. And then at -1, it's at 1/2. At 0, it's at a height of 1. Its y value is 1. At 1, it's at a height of 2. At 2, when x is 2, the y value is 4. When its x value is 3, it's all the way up at 8. And then after that, it goes off the charts. At 4, it's already escalated to a height of 16. So this graph grows very rapidly, even though initially it starts, you know what, let me make this even more close to our x-axis because it looks like it's just barely above it, barely above our x-axis, barely above where y would be 0. So with that sketch, now let's go ahead and talk about some of these key features for this exponential function with the binary base of 2. The domain for this function, those are your x values. There is never a moment where it stops moving to the left or to the right. So the domain here is all real numbers. You could also express that as from -infinity to infinity using the interval notation. The range for this function, the y values, what I want you to notice here is that it never goes below this line right here. You see, no matter what happens, when we raise something to a power, when we raise a value to a power, it's going to remain greater than that 0. So the range here is going to be y values greater than 0, never touching 0, because we're never raising it to a power where it would equal 0. You can't raise something to a power and get 0, but a little bit above. This could be written also as from 0 to infinity. Oh, and you know what? I want to change colors. I want to make this blue. And let's make this one green. Okay, now the end behavior. What happens at the ends of this graph? As x approaches infinity, that's over on this side. This is as x approaches infinity, that's going in this direction, moving in this direction. What is happening to my graph? As I'm moving, if I were to imagine being a little ant on my graph, or just even a person, just traveling on my graph, going in this direction, moving to the right, what's happening? My graph is going up, 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 up. That is going up all the way to infinity, positive infinity. However, if I move in the other direction, that's to say, if I'm going to negative infinity, if I'm moving in that direction, my graph doesn't keep going down forever like a linear function. No, it is flatlining. It kind of just hovers above that x-axis. And so what happens here on this side is it's approaching 0. It doesn't actually ever touch it. It just approaches it. the y-intercept of this graph, that's where it crosses on the y-axis. This right here is the y-intercept. And that y-intercept is at the point when x is 0, y is 1. And the asymptote. Now, this is a word that is pretty new to us as students in algebra. The asymptote is that line that your graph is approaching but not touching. And so what is the equation of that line? It's that dashed red line. It is the line y equals 0. It is that horizontal line. Remember, if it's horizontal, we always write it as y equals. It's a horizontal. It's that horizontal dashed line that you see right here, where your graph is tending above. So that is your exponential function with a binary base of 2. Now, I want us to look at our exponential function with the common base. The common base is a base of 10. And we see this one a lot because we actually work in a base 10 number system. Think about this with me. How many digits are in our number system? We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. All of these digits create any number in our number system. And there are 10 numbers here. There are 10, I should say, digits. So yeah, we work with our common base all the time because it's the number system that comprises the system that we work with. So let's go ahead and graph it. Grab that graphing calculator, do a little split view here. So now we're going to change our base to 10, and raise that to the x power. Again, it's going to look a lot the same, but you might be able to see here how things have kind of changed a little bit, right? It has become much steeper. Our base has changed, and therefore the steepness of this graph has as well. Let's look at the table to see more clearly what happens here. Okay, over here in the negatives, oh, what is that? 0? No, not quite 0, just a value very, 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 very close to 0. In all these negative values, it is just hovering ever so slightly above that x-axis. But then we get to 0, and it's at a height of 1. So I'm going to go ahead and plot that point. At 0, it's at a height of 1. And then at 1, it's already at a height of 10, which is the very top of our coordinate plane here. At 2, it's at a height of 100. So that is blown off the graph. We cannot see this. It grows so fast. So it goes from being flatlined. Let me zoom in. It goes from being flatlined right here. Like if we didn't know any better, we'd say it was on the x-axis. And then it grows so fast, just like that. I love this capability. I can change the color. I'm going to make it stand out a little bit more by putting it in blue. So let's talk about the key features here for this function. A lot alike from what we saw above. The domain of this function, those x values, well, it's fine. We can plug in any one of these values for x. It doesn't, you're allowed to plug in anything for x, no problem. You can raise it to any power. So that means that the range is all real numbers, or you could write that as, and make that a little cleaner. The domain is all real numbers, or write that as any value from negative infinity to infinity you can allow. Now, what about the range? What about those y values? What about those y values? What are allowed there? Well, again, this graph is hovering above the x-axis. So It's going to be all those y values that are greater than 0. That's to say that it's from 0, above 0, all the way up to infinity. The in behavior, again, performs in the same manner. As you're moving in the positive direction, it's growing up and going up and going up and approaching infinity. However, if instead you're moving in the opposite direction, then you're going to be approaching where we have that asymptote. And what is that asymptote? It is this little red dashed line. And the equation of that line is the line y equals 0. That's our asymptote. That's what it is approaching on the left side. The intercept, again, our y-intercept where it crosses on the y-axis is at 0, 1. So do you see how everything lines up the same? Everything lines up the same. The only difference here is the way that it grows each and every time. And now let me just leave you with this idea of how things are growing here. As you move from one point to the next, how is it increasing in height? From here, this point right here is the point. Actually, let's make a little table over here. This point, one of our first key points is this point 0. Let me make. We have the point when x is 0, y is 1. And then we have the point when x is 1, y is 2. And then we have the point when x is 2, our y is, where is it? It's at 4. And then when it's at 3, the y value was at 8. And that was all we were able to graph. Now here, for this function, when we have the base 10, at 0, it's at 1. That matches. That was the same for both of these, right? We had 0 and 1, 0 and 1. That's where our y-intercept is located, right? That's where that y-intercept is. But then what happens here, at 1, it's at 10. 2, it was going to be at 100. 3, it was going to be at 1,000. So what is happening each and every time here? What is occurring? How is our rate changing? It's not changing by adding the same amount each time, but it's changing by a similar factor each time or by a similar multiple each time. Here, each time, it's multiplying by 2, which was the base. And here it is each time changing by a similar factor, multiplying by 10, which is the base. So that base is going to be indicating the factor or the multiple, the amount at which our exponential function is increasing or decreasing over time. So that, ladies and gentlemen, is it for this video, a little introduction to graphing exponential functions. We've seen 2 of the kind of parent functions. We'll look at one more in our next video. And until then, stay fired up.